So today we're going to be looking at linear combinations and regression. Okay. So objectives for this lab activity: you need to be able to describe what a linear combination is. You need to be able to describe what the method of least squares is. You need to be able to do linear regression using Excel and properly report the results of a linear regression based on the standard errors. Okay, so let's look at the first thing we need to know. What's a linear combination? Well, we often encounter data where the relationship between the x and the y values, so these are things you would measure, can be represented by an equation of this form right here. Y equals a constant plus another constant times function of x plus another constant c2 times another function of x, and so on. Okay. So C naught, C1, C2, and so on are constants. F1 of x is a function of x. F2 of x is another function of x. So we say that y here is a linear combination of functions f0, f1, f2, and so on. Okay, let me just pause this. I want to make sure. Okay, so you've encountered this term a lot already this semester. Linear combination means constant times function 1 plus another constant times function 2, and so on. Right? The functions f0, f1, f2, and so on are called the basis functions. So this is really c0, f0 right here. Okay. The set of functions f0, f1, f2, and so on is called the basis set. Okay. And the constants C0, C1, C2, and so on are called the linear coefficients. Note that F0 is simply equal to 1 right here. When you say C0 and you don't have an F0 next to it, so that means it's C0 times 1, so that's your F0, right? Now, that C0 right there, the coefficient of 1, the coefficient of F0, is referred to as the intercept. That's the value of y when x equals 0. More specifically, the y-intercept. And the process of determining these coefficients, C0, C1, and so on, is known as linear regression. So let's look at a few examples. Let's identify what we can call C0, C1, C2, and F0, F1, F2, and so on in these examples. So let's say y equals mx plus b. Okay, so I can write that in the form C0 plus C1x. So what's my C0? B, right? And what's my C1? Okay, slope. So the equation of a straight line falls into this category of functions. Okay. And what's my F0? 1, right? So that's my F0. And what's my F1? X. So that's my F1, right? So let's look at the next one. Y equals a plus bx plus cx squared plus dx cubed. Okay, so c0 plus c1 f1 plus c2 f2 plus c3 f3. So what's my c0 here? The constant that's by itself. So that's your c0. c1 will be b, and f1 of x would be is x. c2 is c. f2 would be x squared. c3 would be d, and f3 will be x cubed. Okay, let's take a look at one more. Let's try this one right here. The rest of that, you need to finish that, write your answers when you submit this report back to me in Moodle. Okay, so what about this one? I'm going to call this my y, c minus 1 over p. I'm going to call that my y, equals C0. So my B prime is my C0, okay, plus C prime P. So C prime is my C1, P is my F1, okay, plus B prime P squared. So I'm going to call B prime my C2, and this is C1, and P squared would be my F2. Okay, so that's the idea. If you can write an equation and you can recognize that y is just a constant times a function of x plus another constant times a function of x and so on, it's just a linear combination of functions of x, then we can determine the values of those coefficients, okay, by the linear coefficients by a process known as linear regression. Okay, so fitting a data to a straight line that you've been doing since freshman chemistry is essentially, it is linear regression, but you're not really just limited to two unknowns there. You know, it's a slope and intercept, but you can have the slope you can say is the first coefficient, right? You can have additional coefficients if you have more functions involved in your expression. So let's move on to activity 2, determining how many points do you need to do a linear regression. Now, the most popular method of doing linear regression is known as the method of least squares. In this method, the best set of coefficients are determined by minimizing the sum of the residuals squared. What's a residual? It's the difference between the actual experimental value of y, okay, and the value you calculated based on the coefficients that you determined. So the difference between those two, you can think of that as the error between your calculated curve and your experimental curve. The difference between those two is called the residual. So if you square all of those residuals, because some of those are going to be positive and some of those are going to be negative, what you want to do is you minimize the squares of those to get the best fit. Okay, so you square each residual, take the sum, okay, and like I said here, calculated y is just C0 plus C1 F1 plus C2 F2 and so on. So if you minimize that, how do you minimize something? Take the derivative, right? So in this case, you take the partial derivative of SRS with respect to C0, set that equal to 0. Take the partial derivative of the SRS with respect to C1, set that equal to 0, and so on. And you can derive the formula for C0, C1, and C2, and so on for the best fit. Okay, we're not going to do that. We're just going to, Excel does that for us automatically, so we can and determine those C's. So we just use Excel as a black box. Okay. So to minimize, like I said, to minimize the SRS, you need to take the derivative with respect to the C, set those derivatives equal to 0. Now, if you have n coefficients, okay, then you're going to have, you need n unknowns, right? N equations to determine n unknowns. Remember, our goal is to determine what those coefficients are. Those are your unknowns. So that means in order to get n equations, n of these expressions right here, okay, then you're going to have n data points. Okay? So now, one thing you do need to be aware of is when you're doing this linear regression, okay, you're assuming that errors in your experimental x values are negligible, which is often the case, because that's an independent variable that you can deliberately set, and usually that's something you can measure or set very precisely. Okay, so given a set of experimental data x1, y1, x2, y2, and so on up to xn, y sub n, okay, your best coefficients basically you would need how many unknowns? You have n unknowns. You have n data points, you can get n unknowns, right? So you just solve your simultaneous equations. Now, most of the time, typically what you want is you have more data points than unknowns. So you have what's called an overdetermined problem, right? So in that case, in fact, that's typical scenario that you'll be faced with. So if your equation has m plus 1 unknowns, let's say your y is c0 plus c1 f1 plus c2 f2 and so on up to c sub m f sub m. So you have, okay, 1 through m, that's m unknowns plus 1, the c naught. So you have m plus 1 unknowns, okay? So the number of data points that you need is going to be, must be larger than m, greater than or equal to m plus 1, okay? So if you have y equals mx plus b, how many data points would you need minimum to determine m and b? 2. 2 points determine a line, right? If in fact you have 2 points, you know, you can calculate exactly what m and b, 2 equations and 2 unknowns. So you need at least 2, right? Greater than or equal to 2. If you have y equals a plus bx plus cx squared plus dx cubed, how many data points would you need? At least 4. If y equals a sine x plus b over x, where a and b are constants, how many would you need? At least 2. Okay? So the number of data points you need to determine your linear coefficients would be at least equal to the number of coefficients that you have to determine. So here in your handout for activity 3, I gave you the procedure for doing the linear regression in Excel. So if you have Excel 2000, this is the procedure, and then this is the procedure for Excel 2007 and 2010. All right, and so I'm going to demonstrate that with this data for free fall. You have y, here's a distance, so we're going to call this our y, and t is time. And we're going to fit this to an equation y equals, you've seen this in physics, right? V naught t plus 1/2 gt squared. What's our C0, C1, and C2 here? C0 is 0, right? What is our C1? V naught. What is our F1? T. What is our C2? 1/2 g, and our F2 t squared. Or you could say your F2 is 1/2 t squared and g will be your C2. It doesn't really matter. Okay? So if you're going to set it that way, so y is, x is time, right? So F1 is t and F2 is t squared, and your linear coefficients are C naught is 0, C1 is V naught, and C2 is 1/2 g. Okay, so let's do the linear regression for this. What you need to do in Excel is as follows. You tabulate your x and y values first. So let's tabulate those numbers. Make this bigger. Okay, so I'm going to tabulate distance here and time. So 0, 0, 0.05, 0.1, 0.15, 0.2, 0.250, 0.3. And to set the format, if you want to make it look pretty, format number of decimal places, 3 decimal places. There, okay. And time is 0, 0.0496, 0.0852, 0.1138, 0.1391, 0.1614, 0.1820. Okay. I'm going to wait till you're all caught up. I'm going to pause this recording for now. All right, so let's continue. So we have our y is distance, x is time. What is our, we need to tabulate F1, which is what's our F1? That's just time, right? So we don't have to actually do that. But normally, it might not be what your variable is. So let's just make sure that we do it systematically. So let's tabulate F1 here. And you know that this is just equal to time, right? And let's tabulate F2, which is going to be time squared, right? And by the way, if you want to do a superscript on for an entry here, you just say highlight that 2 right there, right click, format cells, superscript. And then this F2 right here, if you want that 2 to be a subscript, right, highlight it, format cells, subscript. Okay, and this F1 right here, I want to make that a subscript. Right click, format cells, subscript. Okay, so what would these numbers be? F1 will be just time, right? So I'm just going to equal to this number on the left. So, and then I can just copy that down to the rest of my cells. So that's just the same number as column B. That's your T, right? What is T squared? Equals whatever the number on the left is, B2 is, you square it, right? How do you square things in Excel? Caret and then 2. So shift 6. And that's T squared. All right? So you have a column of F1, a column of F2, and so on. If you have an F3 and an F4, you put that next column right there in the next, just right next to each other. Okay? So what do I do next? I go to data. All right? And you do an analysis. Oops. Data analysis. Where is data analysis? It's not. Yeah, it should be over here. I don't see it on this one. No. Data. Data tools.
Next to outline, like it's a tab next to outline, but it's not there. You can see it.
Yeah, it should be back here.
Press right, click it upside down, like all the way, no, right next to outline.
Next to
All
outline.
the way next to outline, right? Scroll over.
Right.
This tab right here, I don't know if you can click that, no?
Yeah, I know it's over here on this side.
Maybe we need to zoom out. Yeah, zoom out down here.
Something wrong with this. Maybe it's not set up. Okay, so if in case it's not set up on your Excel, you go to options, Excel options, okay, and then go to add-ins, okay, and then analysis tool pack should be installed. Okay, it's not installed on this station. Okay, so you need to manage your Excel add-ins. So you manage your add-ins, hit go, and then you have to make sure you check analysis tool pack. So if you don't see analysis on your Excel, like the one at home, if you have Excel at home, you don't see that at home, then that's what you need to do. Okay, so hit OK. And now if I hit data here, it should say data analysis right here on the right. Okay? So click data analysis and then find regression down here. Let me zoom in on this again. Okay. So what was it I had to do? Data analysis, find regression from the data analysis menu, hit OK. And now you tell it where your input Y range is. So this input Y range right here, you point to the Y values, which is going to be our distance, right? So 82 to 88 for this one. And then your input X range, you highlight the F1 and the F2 columns. If you have more than one function, more than two functions, you highlight those. So like if you have F3, F4, F5, and so on, you highlight all of those. But since we only have F1 and F2, we're just going to highlight these two. All right? Now, you decide whether you want to force your constant to be 0. Constant here refers to the intercept, C0, C0. You can force Excel to set it equal to 0. But if you know it should not be 0, if you don't know if it should be 0, then let Excel calculate it. Now, should it be 0 in our case? What was we know it should be 0, right? So we can force it to 0. So that constant right there, that's the intercept. We're going to force that to 0. And then when you hit OK, it's going to give you the result in a different sheet. So if I hit OK, it comes up with, okay, look, we had sheet 1, we had our original numbers in sheet 1, okay, sheet 2, sheet 3, that's how Excel comes up by default. It created a new sheet, sheet 4, where it puts the results of the regression. Okay, and let's examine these results. And the important thing to look at here is down here. Okay, this right here is the intercept, that's C0, and you force it to 0, so Excel has no choice, it gives you a 0. Okay, x variable 1, this is the coefficient column. The coefficient for x variable 1 is this number right here. So that's your C1. So according to this, what is C1? 0.76187 and so on. The standard error for C1 is 0.00319, so plus or minus 0.0032. Okay, or if you really should just stop with the first non-zero digit. So your uncertainty starts in the thousandths place, the third decimal place. So how should you round off your C1? It's 1, 2, 3, third decimal. 1, 2, 3, third decimal. You should round off there. So you should report your C1 as 0.762 plus or minus 0.003. Okay, what about your C2? The coefficient for x variable 2 is this one right here, C2. So we say that C2 is equal to 4.8712 plus or minus, this is 0.02. So how should I round this off? This is 4.87, so I drop off the 1 and 2. So C2 is 4.87 plus or minus 0.02. So that's how you do regression in Excel. Okay? All right. So what was our C1? Plus or minus 0.003. And what should be the unit for C1? That's C1 is that one, V naught, right? So that should be meters per second. And our intercept was plus or minus. And the unit for that is meters per second squared. You should be able to work that out, right? Meters per second squared. Now, what is our acceleration due to gravity? The goal, presumably, of this experiment is to determine acceleration due to gravity. We said C2 is equal to 1/2 g, right? So g is equal to 2c2. So 2 times 4.87 meters per second squared. And that's going to give you 9.6474 meters per second. Okay? Now, how am I going to propagate the error here? You remember propagation of error from last time? Okay, so partial of g with respect to C2. Okay, so delta g, right, squared is equal to partial of g with respect to C2 delta C2 squared, right? So delta g will just be the absolute value of partial of g with respect to C2 times delta C2. So what would that be? What's partial of g with respect to C2? Actually, we don't need partials since we only have one variable here. But so this is going to be equal to 2, right? And what's delta C2? Uncertainty in C2 is 0.02. So that's 0.04. So your acceleration due to gravity according to this is 9.74 plus or minus 0.04 meters per second squared. Okay. So whenever you have to do regression with your laboratory data, I expect you to give me uncertainties. And if you need to calculate something based on those coefficients, I want you to be able to propagate those uncertainties into the final result. Okay? Yes, V naught is C1. This is actual data from a physics lab experiment that we did years ago. We had this thing, a picket fence type thing where there's a series of black and transparent stripes on the plexiglass, and then we dropped it, run it through a photodiode, a photogate. So as those transparent and opaque stripes pass through, it can calculate these different.
Why would partial G over partial C 2?
It's like saying y is equal to 2c. So what is dy dc? Let's say y equals 2x. What's dy dx? Same thing. When you say that g is equal to 2c2, derivative of g with respect to c2 is equal to 2. Okay. Anytime you're stumped about these derivatives, just think of x and y. It makes it easier to do it. All right. So, we just did this right here. So what was our v naught? Plus or minus 0.003, and our g is 9.74 plus or minus 0.0. Okay. Now let's verify this relationship. Let's create an XY chart in Excel, and let's add a quadratic trend line to that. Okay. So what are we plotting? Get rid of all of the. Let me go back to sheet number 1. I'm going to plot distance versus time, right? So I'm going to insert a chart, scatter plot, okay, and Excel's trying to figure out what to graph for me, so I have to override, select data. So I go to design, select data, and then just remove the series, okay, and then add the series. What is it we want to plot? Distance versus time, right? Or is it time versus distance? No, distance versus time. So our distance would be y values, and our x values would be time only. What happened here? Why do I have? Okay. Do I have the right time? Okay, let me do it again. Design, select data, remove this one, this one right here, this time right here, I also have to remove that. Okay. So now I don't have anything. So add x values would be time, and y values would be distance. All right. And this is my graph. Don't need the legend there. All right, so you should know how to do all those labels and stuff. Let's just focus on doing the trend line for this. This is a quadratic relationship, right? So what you do is you right-click on your data point, one of your data points, you add the trend line, and so you can add a polynomial trend line. Second order means quadratic, right? And since we want to guarantee that our trend line goes to 0, 0, we force our intercept to 0 right here. Okay, and then you can display the equation on the chart. All right, and you can display r squared if you want to see how good the fit is, and there's your equation. So Excel can give you the numbers you want. What is the coefficient of x squared? C2 is 4.87, right? And what is C1? 0.762. Now, note that by default, Excel just puts up numbers that may not have the right numbers to fix. So you need to fix this up. So what you do is you click on it, you can edit it. Okay, so now it's not really y you're plotting, it's d, right? And what is 4.87? That's half of the acceleration due to gravity, right? So it's actually 1/2 of what? 9.74, right? Meters per second squared. So you can write it that way. And it's not really x, but it's t, right? And then highlight that too, right click on it, format, set the font to superscript, all right? And 0.762 should be 0.762, and what's the unit for that? Meters per second, and x is really t, right? See, that's a better way to show the equation on your chart. To do the quadratic trend line, okay, let me take it. You go to right click on one of the data points. Okay, let me just get rid of the trend line first. Right click, add trend line, and then select polynomial second order. Okay, and then force your intercept to 0. Okay, if you want it to go to 0. If not, then leave it as is, leave it unchecked. Okay? And there it is. And then you do if you want to format your trend line, you can show the equation. Display the equation on the chart, and there's your equation right there. Drag it, and then you click on it, you can edit it. Superscript. Let's say I want to do meter per second squared, like that. If I want to do a superscript for that too, I just highlight it, and then right click, font, superscript. For cells, you go to format cell, but if you're in here, just font. All right, and of course you should know all the other things that a graph should have. You should have labels for the x-axis, the y-axis, and all of those things.
That's all. You have put other things for another.
Yeah, what I did was, I know this isn't really y, this is distance, right? So I can call that d. And this isn't really x, it's time, so I could call that t. And that's t. And I have to fix it up so that it has the right number of sig figs. So you can show it like that, or you can show it as 1/2 of the, that should be 4.87, right? So you can show it like that, or you can show it as 1/2 of 9.74. Now, I forgot, this thing should have a unit also. 0.762 meters per second. That's your V naught. Okay? So I'll give you a little time to get caught up. Okay, so let's continue. You'll notice that for your trend lines, Excel only gives you a limited number of possible functional forms. Okay, so we just got lucky here that we have a polynomial. Right, so we can do that with Excel. Now, what if your equation is not a polynomial? Then you're gonna have to calculate your line. You have to manually calculate, or well, you let Excel calculate the trend line for you. Okay, so in some cases, you'd have to calculate the trend line yourself and then overlay it on your data. So I'm going to do that. All right, so I'm going to get rid of this trend line right here, delete. I know my coefficients, right? These are my coefficients, so I'm just going to copy that. I'm just going to say, all right, I know my C0 is 1, 0. So I know my C1 is how much? I'm going to put my C1 here. So this is equal to my C1, which is, I need to get rid of all of these first. Get rid of all of these things I've written here. All right, so this is my C1 and my C2, right? So my C1 is, I'm going to say, is equal to this number right here. What happened? Okay, so there's my C1, it's 0.761. And I'm going to put my C2 here just so I can see it. And that's equal to, I'm going to point to the value in C4. And so there's, what's happening with Excel here? There it is, 4.87, right? Okay, so if I don't have that predefined function in Excel for doing trend lines, what I can do here is I can calculate the trend line myself. Okay, so I want to calculate it from, let's say, 0 to 0 to 0.3, right? But if I want a smooth curve, I don't want to just calculate it at these data points. I want to calculate it at a lot of points, right? So I'm gonna put distance here, and I'm calculate the time here, right? So I'm gonna start from 0 all the way to 0.3. So if I want to split that up into 100 data points, what would that be? What's the step between data points? 0.3 over 100, 0.003, right? So maybe 0.003, or you can say 0.01 times the maximum that I want, which is 0.3. You can type here equals 0.01 times 0.3. That's 0.003. Okay, so I'll retype that 0.003, and then I'm just going to drag that down so that I get values all the way up to 0.3. Okay, so I'm going to stop at 0.3. So that's my distance, and then I calculate the time for that. What's the value? It's equal to V naught, which is, this is V naught, right? And this is 1/2 G. C2 is 1/2 G. So V time is equal, distance equals, all right, we got it mixed up. Yeah, but I do have distance in terms of the t's, right? So what I'll just do is I'll set up my time, and then I calculate the distance instead. Okay, so my time, sorry about that, and calculate my distance. So I'm going to go from 0 to 0.182. I do have this versus time, so my x-axis is time. Right, so 0 to 0.2. Okay, so I'm going to go 0, 0.02 all the way to 0.2. Okay. There. So I get rid of all of this. And I can calculate my distance after. What happened? Oh, oh, it's not my day. All right. What happened here?
I think it's taking a second to catch up.
All right. Okay. So I'm going to go 0, 0.02, and so on, right? So I'm going to copy that down to get to 0.2. I'm already at 0.5, 0.18, 0.2, right there, right? It's not a whole lot of data points. Maybe I should go 0.002. Okay, so 0.002, and then copy that down until I get to 0.2. There, okay? And I calculate the distance. What's my distance going to be? Equals V naught, which is this one, times time, which is this one, plus 1/2 g, which is this one, right, times time squared, which is this one squared. So this formula is, look, B10, which is V naught, times time, which is B14, column B, row 14, plus 1/2 g, which is B11, times B14 squared, that's T squared. Got it? And so since I want to copy that down, when I copy it, I don't want B10 to change, and I don't want B11 to change. So I put dollar signs in front of the B and the 10, and B and 11. Okay, so copy that down. Let's make sure it copies correctly. All right, so this is B10 and B11. Okay, so copy that down some more, all the way to the bottom. There. Okay, so now, I'm sorry. Okay, equation is, let me make that a little bigger. This one is B10, which is the value of V naught, times B15, which is the time, which is the column B, plus B11, which is the value of 1/2 g, times B15 squared. So this is for the entry in A15. If you're doing the entry in B14, in A14, that's what you have. So now what do I do next? All I have to do now is add this to my chart, okay? So if I add that to my chart, I go back to my chart, okay? I think you need time to get caught up. Okay, let me pause. All right, so what I need to do now is go back to my chart, click on design, select data, and now I add another series to my chart, okay? And this series is going to be my fitted curve, so my x values would be time, I like time, and my y values will be distance, the calculated distance. Right, and there it is. Hit OK, and there it is. It's all over. It's covered up all my data points. I want my trend line not to show up as data points. I want it to show up as a smooth curve. So what do? I click on it and format my data series. Okay. Marker options, I don't want any markers. So that makes the thing disappear. Okay. My line color, I want a solid line. Okay. And let's see what happens. There it is. I've got a solid line and no markers. And I have my data points right there. Let me format that to a different color. I want my line to be red. Right. You can see there's your data points, experimental data points, and then your fitted curve. Right. I probably want to make your line a little thinner. So marker line style. You can change the thickness. Let's see, line mark. Oh, that's the marker line. This is the line style. I want to change the thickness. Right there. See, much better looking. Okay. So that's how you draw your own trend line. If Excel doesn't have one of those predefined trend lines that you want, then you can make up your own. So for the rest of this lab, so that's what we just did. Okay. For the rest of this lab, okay, I've given you data from the photoelectric effect. Okay, this is from Atkins, from the textbook. So we're going to fit kinetic energy. We have kinetic energy data in electron volts versus wavelength. Okay, and the relationship for the photoelectric effect, if you remember, kinetic energy is equal to the photon energy, which is hc over lambda, minus the work function. Right? So what's our y here? Ke, and what's our x? F1 would be 1 over lambda. So hc is going to be, we're going to pretend we don't know hc. Actually, we're going to use we'll use c over lambda. I think I did tell you to use lambda as x. All right, we're going to use f1 as c over lambda, right? Make things easier because we want to use this to determine h. So we're going to use c over lambda as our f1, and h is going to be our unknown coefficient, c1. We're going to pretend we don't know Planck's constant. And this is what? C2, C naught, right? C naught is negative 5. That's not a function of lambda, see? So that's your F0. F0 is 1, right? Okay. So this is really just a straightforward linear regression, equation of a straight line. So you need to figure that out. Okay. So we're going to you have to look up the defined value for the exact defined value for the speed of light. So we're going to assume we know that, okay? And we're going to use our data to figure out the value of Planck's constant. And the value of Planck's constant is just going to be C1. And then for your second post-lab question, the Balmer series of spectral lines from hydrogen, you can fit that into this equation right here. 1 over lambda is equal to negative r times 1 over n squared minus 1 over 4. Okay, where n is just an integer, 3, 4, 5, 6, 7, 8, 9. So these are data obtained from this line spectrum of hydrogen. Okay. And so this time around, your goal is to determine R, the Rydberg constant. Okay. This is known as the Balmer equation, and constant R here is the Rydberg constant. And I want you not just to fit it, but actually draw a trend line through your data, the necessary trend line. Huh? Yeah, calculate. You might need to calculate the trend line for this one. Well, actually, no. This is simple. I think you don't need to. It's one of the predefined ones. It's because you've only got how many unknowns here? It's really just 2, right? C naught and C1. What's our C naught going to be? You can rewrite this as negative r 1 over n squared plus r over 4, right? So what's our C naught? C naught, this is our C naught, and you can call this your C1. So this is just a straight line graph. Okay. And then the third question you want to work on is this fitting of the vibrational energy levels versus quantum number V. Okay, so this should be lowercase v. 0, 1, 2, 3, 4. The vibrational energy is given in reciprocal centimeters. Okay, these are the numbers. Okay, so you have to determine these constants: omega e, negative omega e x e, omega e y e, and omega e z. from the data. These are values for HCl. You'll encounter this later this semester when we talk about spectroscopy. Okay, so this would that's the third problem you need to work on for your reports. Okay, and that should be it for this one. So due on Wednesday next week. So work on it.